Section 8.6 is integral tables. You will be allowed to use an integral table only for the first page of your exam because I don't want you to have access to this for every problem on your exam. Otherwise, I wouldn't test whether or not you know how to integrate anything on your own. I have a copy of an integral table that I've pulled up, and I did put this in Brightspace. So if you lose the one that I just gave you, you can always find it on Brightspace. I want you to pay attention to how the table of integrals is organized. The first few are just the basic integrals that you should have memorized by now. And then we start looking at ones that are with forms involving ax plus b, a squared plus x squared, a squared minus x squared minus a squared. And there's trigonometric forms. And then I think we go into exponential forms. Nope. Still trig functions, bunch with trig functions, inverse trig form, and then your exponential and logarithmic forms. And what these do is they provide a pattern that we can use to take complicated integrals and actually solve them. There's a variety of these, and we'll be using all of these. Well, actually, no, we won't. We won't be using all of these forms. Whenever you're doing your homework or working on the test, you just got to decide which form it is that you need. So let's look at this first problem. In example 1, we're asked to use the integral table, and we've got to look for what form is this? What does this look like? You know, it's clearly not a trigonometric form, so what form? Look at your table of integrals and see if you can find a rule that corresponds to an integral in this form. Let's look at 29. It looks like 29b. So looking at rule 29b, this looks like our integral, and we found this under the forms containing ax plus b. Even though there's subtraction there, if you're adding a negative, then b would just be a negative. So it looks like it's going to be this one right here that we're going to use. So we have the dx and the x. A would be equal to 7, and b would be equal to 1. We could have used a, it's just that b would have been equal to negative 1. But since we have this form with a negative in it, we're going to go ahead and use that. So it looks like this is going to be the form. The first thing you want to do is identify what is it that you're going to plug in place of the letters over here on the right-hand side of the equal sign. So we're going to substitute the numbers into the rule and then simplify the results. So the rule is this is going to be 2 over the square root of b tan inverse the square root of ax minus b over b plus c. And all we do is we drop in a 7 for a and a 1 for b. And when we do that, that's going to give us 2 divided by the square root of 1 tan inverse the square root of 7x minus 1 over 1 plus c. And then we need to simplify this. The square root of 1 is 1, and 2 divided by 1 is 2. So this is going to be 2 tan inverse the square root of 7x minus 1 plus c. And I would not have wanted to try to evaluate this integral without using the table of integrals. The table of integrals will be your friend for this section. Do not try to do these problems without them. Now, it is possible to do some problems without using the table of integrals. Actually, it's possible to do a lot of them. But when the table's there, it makes life easier, so use the table. And if this were a test problem, I would want you to tell me that you used Rule 29b. Always tell me which rule you use. Now, this table is not the exact table that goes with your book. I want you to use the table that I provide and use the rule number according to what I provide. I have yet to figure out what table your book is using because whenever I've looked at the instructor's manual to try and figure it out, they don't match up with these numbers. And the irony is I took these from a Pearson book. It was just an older edition and they didn't match up back then either. So use the tables that I give you. All right, example 2. This one involves trig functions, so we need to try and find a rule that uses an inverse trig function because cosine inverse means that you're going to look for a cosine inverse function. It does look like rule number 107. So it looks like rule number 107 will fit. We have an x to the first power, so n is going to be equal to 1. And then we have cosine inverse ax, so a is equal to 6. And then we have this extra 6 right here. What do we do with that extra 6? We can rewrite this as 6 times the integral of x cosine inverse 6x dx. Now our integrand looks just like the integrand over here where n is equal to 1 and a is equal to 6. But because this 6 is out in front of the integral, you don't want to forget about that. So when we write our answer up, looking at the right-hand side of this equals sign, I want to make sure that that 6 stays out front. So that's going to give us 6, and then this is going to be equal to x to the n plus 1. N is 1, 1 plus 1 is 2. So that's going to be x squared over n plus 1, and 1 plus 1 is 2. Cosine inverse 6x, because a was equal to 6, plus a, which is 6, over n plus 1, which is 2, times the integral of x to the n plus 1, which is going to be 1 plus 1 is 2, dx, over the square root of 1 minus 6 squared times x squared, so that's 36x squared. And I don't put a plus c because I still have an integral in here. This is a recursive formula, meaning that we're not going to be able to get our final answer from it, but it's going to work it down to an integral that we should know how to integrate, or can even look up another rule for. Our next step then is to simplify this. So the first thing I'm going to do is distribute this 6 across and simplify. So that 2 will cancel in with that 6, giving me 3x squared cosine inverse 6x plus, that's going to be 6 times 3 because 6 divided by 2 is 3 times 6 is 18, integral of x squared dx over the square root of 1 minus 36x squared. Now you have a choice. We can either practice a skill that's going to be on our test, and that's using the trigonometric substitution, or we can go to our table and look for another rule that we can use to simplify this. So for trig substitution, the first thing I'm going to want to do is set up a right triangle. So there's my angle theta, and there's my 90-degree angle. What is the hypotenuse going to be, looking at this integral right here? The hypotenuse is going to be 1 because the 1 is listed first for subtraction. If you need to review trig substitution, go back and watch the section 8.4 video. Where's the radical going to go? Is it going to go on the opposite side or the adjacent side? Adjacent. So my radical goes down here. And what is the opposite side going to be then? 6x. Now that I have my triangle set up, I need to figure out what x is going to be equal to, and dx, and the radical, and all that good stuff. So if I look at opposite over hypotenuse, that's going to give me 6x over 1, which is just 6x. Opposite over hypotenuse is which trig function? That's equal to sine theta. So that means that x is going to be 1/6 sine theta. And what is dx going to be? 1/6 cosine theta d theta. The derivative of sine is positive cosine. So I know what I'm going to plug in for x. I know what I'm going to plug in for dx. I need to now figure out what I'm going to plug in for the radical. Well, that radical is on the adjacent side, and if I put that over the hypotenuse, I just get the radical, and that radical is 1 minus 36x squared. Adjacent over hypotenuse is which trig function? Cosine theta. Now I'm ready to rewrite this integral. So this is going to give me 3x squared cosine inverse 6x plus 18 times the integral of, in place of x, I'm going to plug in 1/6 sine theta. That was squared, and then the dx is going to be 1/6 cosine theta d theta all over cosine theta. Now I want to clean this up. So this cosine will cancel with this cosine, and I need to square that 1/6. So let me continue this down here. So when I square the 1/6 and multiply by another 1/6, I end up with 1/6 cubed. And then this is going to be sine squared theta d theta. How do you integrate a sine squared? What can we do there? We can use the power reducing formula on this. So this part came down, and then if I take 18 and divide it by the constant 6 to the third, I end up with 1/12. And now I've got the integral of 1/2 times 1 minus cosine 2 theta d theta. So that means I can pull the half out, and that would make this 1/24. I'll do it in the next step. A lot of this stuff is just, I'm dropping it down because it's already done. I'm going to pull that 1/2 out, and that gives us the integral of 1 minus cosine 2 theta d theta. Now I'm ready to integrate this. The integral of 1 with respect to theta is just theta, and when I integrate cosine 2 theta, that's going to give me 1/2 sine 2 theta plus c. Do I want to leave the thetas in my answer? No. If sine theta is equal to 6x, what is theta going to be equal to? Sine inverse 6x. So this gives us 3x squared cosine inverse 6x plus, and I'm going to go ahead and distribute that 1/24 now, and that's going to give me 1/24 sine inverse 6x, because if 6x is equal to sine theta, take sine inverse of both sides, and I get theta is sine inverse 6x. Minus, and now when I distribute that 1/24 across, that's going to give me 1/48. We're going to rewrite sine 2 theta as 2 sine theta cosine theta. But what is sine theta equal to? Looking at your triangle up here. Sine theta is equal to 6x. So I'm just going to clean this up. Sine theta is equal to 6x, and cosine theta is equal to the square root of 1 minus 36x squared. So that means that our final answer here is going to be 3x squared cosine inverse 6x plus 1/24 sine inverse 6x minus 1/24 times 6x. And actually I could multiply that. 6 over 24 is 1/24 times 6x gives me x over 4 square roots of 1 minus 36x squared plus c. And this would be our final answer. The question was, what happened to the 2? Well, I went ahead and multiplied it in my head. 2 times 6 is 12, and 12 divided by 48 is 1/4, so that's where that x over 4 came from. Now, we didn't have to do the right triangle trig substitution here. We could have looked up another formula and just used the integral tables. I just wanted to give you guys some extra practice on trig substitution before your test next week. This last problem that we did was an example of a reduction formula, because it reduced this integral that we didn't know how to do into a problem that had an integral that we did know how to do. So let's look at example 3. This is our integral. We see that it's a trig integral. Is there a rule in the tables that we could use to work this problem easier? We know we could rewrite sine to the 5th as sine squared times sine, and then rewrite sine squared as 1 minus cosine squared, but then we've got to go through all the power reducing formulas. We know this because when we were going over trigonometric integrals, that's what we had to do with a problem like this. But there is a way to shorten this process by using another formula. Rule number 67 seems to fit the bill. Let me go grab it. So for this rule, we need to know what n is equal to, and it looks like for this rule, n is going to be equal to 5. And we need to know what a is equal to, and a here is going to be equal to 7. So now we can rewrite this integral using this formula, number 67. When we do that, that's going to give us the integral of sine to the 5th 7x dx is equal to negative sine raised to the n minus 1. N is 5. 5 minus 1 is 4th. So that's going to be sine to the 4th 7x cosine 7x, because a was equal to 7, divided by n times a. Well, that's going to be 5 times 7 is 35, plus 5 minus 1, which is 4, divided by 5. So this is going to be 4/5. The integral of sine raised to the 5 minus 2 is 3, 7x dx. So when we plug in an n for 5 and a 7 for a, this integral becomes this, which leads us to another integral that would fit rule number 67, wouldn't it? So this time n is going to be equal to 3 and a is still equal to 7. So we're going to repeat another iteration of this. And I'm going to rewrite this first term as negative 1 over 35 sine to the 4th 7x cosine 7x plus 4/5 times, and now I've got to apply the right hand side of this formula again. So that's going to give us a negative. Now n is equal to 3, so this is going to be sine squared 7x cosine 7x divided by 3 times 7 is 21 plus 3 minus 1 is 2 over 3. Integral of 3 minus 2 is 1, so that's just going to be sine 7x dx. I kept this in parentheses because this integral was multiplied by 4/5, which means that I need to distribute that 4/5 across to each of these terms. And when I do that, that's going to give us the following. So when I distribute the 4/5 across to this first term, that 5 in the denominator gets multiplied by 21, which gives us a negative 4 over 105 sine squared 7x cosine 7x. And I also have to distribute the 4/5 across to the 2/3, which is going to give us 8/15, the integral of sine 7x. And we know how to integrate sine 7x, don't we? The integral of sine is negative cosine. So that's going to make this a minus 8/15 times 1/7 cosine 7x plus c. So then we can multiply these two fractions and get our final answer. The first two terms are going to stay exactly the same. I just copy them down. And this would be our final answer after we multiplied the 8/15 times the 1/7. First two terms stayed the same, and we simplify. So you may have to use a formula more than once. You may have to use different formulas in the same problem. We could have done that with example 2. Instead of doing the trig substitution here, if I wanted to stay true to the problems in this section, I would have looked up another formula to evaluate this integral right here. What formula would I have used there? It would have been a form a squared minus x squared. 49. We could have used number 49 on this one, but notice this has a 36x squared in the problem, and formula number 49, let me go ahead and grab it and talk about it for a second. Instead of doing the trig substitution on this formula, on this integral right here, I could have used this formula, but if I would have done that, I don't have an x squared here. What would I have had to have done in order to be able to use this formula? I would have to rewrite this integral and do a trig substitution, wouldn't I? You know what, let's do this added as an added problem. This would be an alternate ending for example 2, so I'm going to call it example 2 star. Remember we were left with this integral in our problem in example 2, and I said that we could solve it using trig substitution, and because I wanted to give us more practice on the trig substitution, that's what I did in example 2. But I want to show you that if we wanted to use the integral tables, I would have looked up number 49, and this does not look exactly like this does. It looks close though, doesn't it? What can I do to this to make it fit this pattern exactly? Well, one thing I can do is something called a u substitution. Here I've got a 6x that's being squared. So I could say let's let u be equal to 6x. So du would be equal to 6 dx. But this has just the x squared, and that's just the x squared. So what is x squared going to be equal to? If u is equal to 6x, u over 6 is equal to x. And then if I square that, that's going to give me an x squared. So that means that I need to rewrite this. When I rewrite this so that it fits the pattern here, I'm going to change this integral into the integral of 1 over 36 u squared times 1/6 du. I have the dx, so I need to say 1/6 du is equal to dx. So this 1/6 du replaced the dx. This 1 over 36 u square replaced the x square, and this is divided by the square root of 1 minus u squared. So now I've got some constants that I can pull out, and that's going to give us 1 over, what is 6 cubed? 216? The integral of u squared du over the square root of 1 minus u squared. Now this fits the pattern where u is equal to x and du is equal to dx. A is going to be equal to 1 and u is equal to x. So when I integrate this using this pattern, I'm going to get 1 over 216, because that's already out in front of the integral, times 1/2 sine inverse, x over 1 is just x, but I'm not using an x, I'm using a u, minus 1/2 x square root of 1 minus, and that's not an x either, that's a u. And this is what you got to watch out for when you do a u substitution. If your formula has x's in it, it's very easy to write the x's, but we've got to use a u. So this is 1/2 u square root of 1 minus u squared plus c. And when we clean that up, or when we go back to the x's instead of the u's, that's going to be 1/2 sine inverse 6x minus 1/2 6x square root of 1 minus 36x squared plus c. And if you'll recall, we had that 18 out front, and this was our 1 over 36, and then there's our half that we saw in front of these. And when we simplified that, we would end up getting the exact same answer with that formula. I'm just not going to take the time now to finish every little detail. I just wanted to show you a formula when you had to do a u substitution. So if we let u be this for our substitution, that means in this formula, a is equal to 1 and x is equal to u. you may have problems on your homework where you have to manipulate the integral first so that it fits the formula exactly. And how you do that is by playing with constants here and use substitutions. Just be very careful keeping track of your variables, because you saw me as I was integrating this, I wanted to write x and I shouldn't have, because my integrals variable was u. All right, and this wraps up section 8.6.